What's up, everybody? It's kind of my first time making a video like this, so honestly, it might be a little bit of a mess. A little busy this time of year, but of course, we're trying to prep for the IB papers. I'm looking at the end of topic 1, combinatorics. We've talked about this. The formulas are here. You can use these. And we never really got into this kind of stuff with complex numbers, and we certainly never got all the way to modulus arguments and de Moivre. So we're going to kind of start by talking about complex roots. Again, this is kind of our first one, so honestly this is going to maybe be one of the easier topics that we go over in a video like this. It's ridiculous. When we need to find all the roots, a lot of times we're just used to there being nice roots all the time. Because this is a power 2, degree 2 polynomial, then there's guaranteed going to be 2 roots for sure. Roots 2. And that's just because there's a square. But if I try to factor this, I'm thinking about a positive 13. That means I either need plus, plus, or minus, minus. The numbers are 1 and 13. Can I make a negative? No, right? And so our factoring fails. And so we need to use the quadratic formula. We've got negative b plus or minus the square root of b squared minus 4 times a times c. That's 40 and 12, 52, all over 2a, which is just 2. That's 4 plus or minus 16 minus 52 is going to be 40, negative 42, negative 36 over 2. It's going to be 46. It's going to be negative 36. Nice. This kind of works out pretty good. 4 plus or minus. Now, we know that the square root of 36 is 6, but we have this negative. We know that's a problem. That creates the I here. And of course, this is actually now a lot easier to simplify. We can divide both of these terms by 2, and we're going to end up with 2 plus or minus 3i. Now, these are my roots. These are called complex roots. This is a real number. This is 2, just a normal old real number, and this is an imaginary 3. It's called complex. It's kind of like, we got complex issues because it's a little bit of a both thing, right? It's some real and it's some imaginary. Now, the thing about complex roots is that they always are in pairs. They always come in pairs. We know that for a fact. They always come in pairs. And that's pretty straightforward. They always come from square roots. Square root of a negative number, and square roots always make a plus or minus. And so they always come in pairs. So 2 roots, and these are the 2 roots. Now, if we just think about this on a graph, this is just a normal Cartesian plane, x and y. This graph is going to be a graph that looks something like this. Now, we know that normally the roots are on this x-intercept. We know that roots are the same thing as solutions, and this does not have any solutions. It does not have any roots. It does not have any x-intercepts. But actually, the benefit of the word roots is that a root will include negative. So even though this doesn't look like it has any x-intercepts, it still is going to pick up those imaginary roots. There is ways that I could graph this more specifically. I know it's a positive order, positive even, so I know it goes up. I know it can't cross through, so I know something like this. I could try to maybe do completing the square, for example, and set up something like x minus 2 squared. That would have to be a plus 4 to match the pattern, so I'd also want to do a minus 4, so I would need a plus 9. So maybe this point right here is 0, 9. That's maybe more in depth than I wanted to go for this question, but all of this is good algebra skills. Now, what if we need to find all the roots for an equation like this? This is a third power, third degree, and so we're working with 3 roots. We know for sure that there's 3 roots. And if we're given x equals 1, that means that we have one of these here. Okay? If we try this out and we plug it in, that's 1 minus 5 plus 9 minus 5. That's minus 10, it's plus 10, it's going to be 0. So this does work. Now, how can we figure out what the other ones are going to be? Basically, we know that when we factor this, one of these factors is going to be x minus 1. That's coming from this root here, but we don't know where the other factor is going to come from. It's going to be an x squared factor of some kind. And we could, try to work backwards. It can be a little difficult to do this. If this is a negative 5, we know that this is going to have to be a positive 5 over here. But honestly, this can be a little bit of a mess. The way that I would go about it is use synthetic division. If I know that my root, or one of my solutions here is negative 1, I could just try to divide it out. Synthetic division is 1, negative 5, 9, negative 5. Now, one of the things we want to remember is when we work with synthetic division, do we put the root on the outside or do we put the factor on the outside, right? Am I supposed to go with a negative 1 on the outside because that's what the factor is, or am I supposed to go with the positive 1 on the outside? If we start with 1, we bring this down, we multiply, we add negative 4, we multiply negative 4, we add 5, we multiply 5, we add 0. It's the root that we want to go with, not the factor. Now, you can see this is already pretty much what I had. This 1 is my x squared, and this 5 is my plus 5. It's this minus 4 that I hadn't figured out here that would go in the middle. So I'm looking at x minus 1, x squared minus 4, plus, that's an x plus 5. Yikes. Now the problem is, here's 1 root, and here's 2 roots. Hopefully I can factor this and find my roots. The problem is, multiplies to make positive 5, but adds to make negative 4 is impossible. Okay, so yet again, we need to find our 2 complex roots. They're going to come in a pair. I'm going to have to do negative b, which is 4, plus or minus square root b squared, which is 4, minus 4ac, which is 4 times 5, which is 20, all over 2a, which is just 2. That's going to be 4 plus or minus negative 16. That's a 4i over 2. And my other roots are going to be x equals 2 plus or minus 2i. Again, that's 3 roots. That's 1, 2, 3. This plus or minus is giving us 2. We could also see it listed like this. X equals 2 plus 2i, x equals 2 minus 2i, and x equals 1. Another way that they could ask this same question is they could say, instead of this, they could say, given x equals 2 plus 2i. Anytime you're given one imaginary root, remember they always come in these like fraternal twins. They always come in these doubles. And so as soon as I'm given this, that means that I know that x equals 2 minus 2i has to be there, because we have to have the bro of the other imaginary number, or a complex number. Now the complex plane is how we can kind of go about graphing these. When it comes to graphing on the complex plane, we're going to try to graph 2 plus 2i onto the complex plane. And if we're going to graph 2 plus 2i, we kind of take the x, which is the real, and so this 2 is going to go onto in the x direction, and this 2 we're going to put on the y direction. And so 2 plus 2y in the complex plane would be right here. This is 2 plus 2y. So it's pretty much, you just graph it the same that you would before. Now, the weirdest thing about doing this a lot of times is that now we're using x and y to graph this. And that means that they don't want to tell you x equals 2 plus 2i because we're already using the x. So instead, they'll tell you z equals 2 plus 2i. And that's to avoid using the same variable multiple times. So if you noticed on this question, we used z's as our letters, and I just totally forgot and replaced them right away with x's. The reason that they've gone with z's is because if we try to plot these points, we're gonna use like xy coordinates, and it's like double dipping on your x's, and so they like to just swap it all to z's. Now this can be relatively straightforward. If we want to graph z equals -3 minus 2i, it literally just means -3, -2, right? Just go -3, -2. Here it is. Now sometimes we start to think about these as like vectors almost, because it's like the directions that we want to go, and so vectors kind of come into play a little bit. And then we have the modulus, and the modulus is basically, you almost want to think of it like the magnitude of the vector, and the magnitude is just the length of the vector. So when I have this 2, 2, the modulus is, how far is this actually to get from the origin to this value. Now, it's the same thing that it always is. The modulus is just the distance formula, okay? The distance formula, as always, a lot of times it'll be like modulus like this. They'll even write it like this, the magnitude kind of notation, and it's the square root of x squared plus y squared, as always. The only thing weird about doing this is that we do have an I in here, but when it comes to plotting it, we've gone 2 and 2. We haven't actually gone I, and so we're not going to include the I in the modulus. So it's like magnitude and make sure that you do no I. Now that means that these moduluses are actually really straightforward. If it's 2, 2, then it's just the square root of 8, because it's 2 squared plus 2 squared square rooted, 4 plus 4 square rooted. If I wanted to find the modulus of this, it's just 3 squared, 2 squared, add them together, square root. It just looks like -3 squared plus -2 squared. Remember, no i's. That's 9 plus 4. That's the square root 13. So I could say like modulus z is square root 13, which pretty much just means like the magnitude of z just means the square root of 13. And the last thing I'll say is, because this is distance formula, because it's the Pythagorean theorem, basically, Pythagorean theorem triples are very popular. So you might see something that says like, hey, z is equal to 4 minus 3i. This 4, 3 is making a little bit of a 3, 4, 5 triangle. If I do the modulus of this, it's going to be the square root of 4 squared plus 3 squared, which is going to be 16 plus 9, which is going to be the square root 25, which is going to be 5, right? This is our 3, 4, 5 triangle. Okay. The last thing I want to cover today in a little bit of our, touch up is polar form. Okay, polar form, it's kind of like the North Pole and the South Pole. If you think about, the globe, and you're looking at the globe from the top, and this is the Arctic, this is the North Pole, you might have this vision of seeing the globe. This is the Arctic Circle, these are like the ice caps, and you have these lines here. These are the lines on the globe that normally go up and down, but we're seeing it from the top. It's almost like this kind of visual really helps me kind of figure out what's going on. Polar form, instead of walking to the side and then walking up, polar form, I always think about it like this. Polar form is like loading a cannon. 2 ends on cannon. I guess 3 ends on cannon. Polar form is like loading a cannon, all right? We've got our cannon, and we're gonna shoot our cannon. I don't know, it's getting worse. Drawing a cannon is kind of risky when you're a teacher. So I'm thinking about it like this. In polar form, instead of walking to the side and then walking up, polar form is about degrees. So instead, your polar form is kind of like saying that you want to load a cannon and you want to launch something at a 60-degree angle, and you want to launch it like 10 feet. Now, that is another way to plot something on this XY plane. But the thing about polar form, and this is the big one, is that it's no X and Y. Polar form is different. Polar form is R theta. The idea here is, in order to get to this point, we need to know the radius and we need to know the angle. So let's say I wanted to graph in polar form and I wanted to graph 1260. Okay, that means I go to 60 degrees and it's 12 long, and gets me right here. If I wanted to graph 2460, that means I go to 60 degrees and I go 24. If I wanted to graph 1230, that means I go to 30 degrees and I graph 12 as my radius. If I wanted to graph 3 and 150 degrees, then I would go load my cannon. Now, this is not drawn to scale, so maybe this is bad. It would be something more like this. So I would only shoot at 3. I wouldn't quite shoot it as far as these other ones that are 12. When you do this, it's the radius of a circle, and so you're never going to see negative numbers as your radius because that doesn't really make as much sense. What comes next, and the things that we haven't talked about, is we're starting to, with these modulus and demoivres, is we're starting to include complex numbers. Notice this Z, which is something that we talked about. And we're going to start including polar forms into it, right? If you notice this R, that's your radius. And if you notice these thetas, that's your angle. Then you can also see we have an I here. So we have a radius with a real component and an imaginary component. That's where we're getting the complex argument. Now, all of this stuff together, it's right in the middle of pretty confusing and easier than it looks. And that's a weird place to be as a teacher, because I don't want to tell you that this stuff is easy. It's certainly not easy. Honestly, I only teach it like 2 days every year, and every time I do it, I have to go back and kind of do a refresher and remind myself how it works, to be honest. But once I do the refresher and I go through it, I'm like, you know what? I think I can handle this. I think that's all that we're going to do as far as this video goes. As far as what we've gone over, hopefully finding roots, including complex roots, you can handle. Hopefully you know that the degree is how many roots you have. Hopefully you know that complex roots always come in pairs. Hopefully this completing the square and graphing, this is from the topic number 2. Hopefully you feel pretty good about that. Synthetic division might be a little bit of a flashback. Finding these other values, listing them this way. Finding the brother of a pair that's given to us. In the complex plane, we just graph them as x and y coordinates. It does get a little sketchy, so we use z to avoid the double x issue. We talked about modulus, which is literally just the distance or the magnitude of the vector, and it's really not too bad. And of course, we wrapped up talking about polar form, which sounds kind of crazy, but it's literally just a radius and an angle. It really isn't all too bad. Okay, I think what I really hope is to give you tomorrow also a little bit of work that you can do as optional homework to maybe practice some of these techniques, and then we'll just continue to build our ability for some of these more obscure topics. But all right, hope this works.